Welcome to section 2 of unit 4, where we've in the first section defined orthogonality and looking at the relationships between subspaces and orthogonal subspaces. And now we're going to start looking at projections and how projections use orthogonality. I feel like I'm going to film this like 5 times. And how they connect to lines and subspaces. And I want to use this first part of the video sessions to really go over his introduction to the section, because I do think there's a lot going on in the section. And then that way we can focus in the second part, specifically projections onto a line, and looking at the algebra and the formulas, working through the examples that you see in the textbook. And then in the third section, moving into projections onto subspaces when he builds it out into matrices. And just kind of using this video again as going over his introduction to hopefully just help add and express just up on the board kind of the overarching ideas. Specifically just in the example and this kind of the special case that he gives of what are the projections of B equals to 2, 3, 4 onto the z-axis and the xy plane, since we can easily kind of conceptualize that. And then that leads into the projection matrices P1 and P2, capital P1 and P2, that would produce those projections onto a line in a plane. In other words, if I want to take any vector B or any, really any vector in the space, if I want to project it onto a line or on a plane, what matrices would produce that for us? And so just to begin, let's say we are looking at 2, 3, 4, and I've got this rough sketch, and you see this in the text, and I want to look at this in terms of the projections onto the line and onto the two-dimensional space. And the projections that he chooses is looking at this vector B and projecting it onto the z-axis first. That's my line, so it's my dimension 1 space. And again, the idea of a projection is kind of like a shadow. If I was to shine a flashlight or some kind of source of light at my vector, I'm essentially just looking at the shadow, like how much of this vector is in the direction of z. That's essentially what I'm trying to find out. If you've worked in physics and you've worked with vectors, we're essentially finding one of the components to the vector b. Specifically, notice in this case, it's the z component for this vector. And I want to try to find this projection. That's the idea. I want to project this vector onto z. And when I'm looking for that projection, I'm looking for what is the multiplier P1 on B that would produce just that vector in Z, 0, 0, and then whatever Z is. That's what I'm essentially looking for. And because of the simplicity of the problem, because it's a 2, 3, 4 vector, you can kind of see that this projection would be exactly at a height of 4. And so the vector that's only in this direction that would create that projection would be 0, 0, 4. And so if I'm looking for what do I need to multiply with B to create this vector, we're looking at, let's see if I've already writing this the right way. That is my projection. That is my P1, is 0, 0, 4. I was writing this wrong, excuse me. That is my P1. So whereas the vector wouldn't make any sense. So P1 would be 0, 0, 4. Versus P2, I'm looking at the two-dimensional space, which is the xy plane. And now I'm looking at the projection straight down into this two-dimensional space, where I'm creating a two-dimensional vector. And that projection would result in 2, 3, 0. So this is my projection onto a line. This would be my projection onto the xy plane. Again, the projection piece that we're looking for is that not resultant vector, but that component vector is how I kind of think about it. So it's almost like you can kind of see that B is created by traveling this vector in the xy space and then adding to it z, which would be the 0, 0, 4. And this is kind of that very first part. I want to try to find these projection pieces. But once I find these projection pieces, I want to know, like, how do I multiply with B to get this answer? What do I multiply with B to get this answer? And this is what I initially started with. And if I'm having a vector that is a 3 by 1 vector, to create a 3 by 1 result, I need to multiply this by 3 by 3. In other words, we're trying to find the matrices P1 and P2 that would create these projections with B. And when I'm looking specifically here, notice how we want to keep the third component, but I don't want the first two to maintain that projection. Then my matrix P1, capital P1, this is essentially lowercase, would need to be essentially the identity matrix where the first two columns are all zeros and the last column is the last column of the identity matrix, because this would tell you, okay, I want 0 in the first entry, 0 in the second entry, but I want whatever your third entry is the same. And so if I do this multiplication, notice row, column, zeros, row, column, zeros, row, column gives me that 4 entry. This will create the projection. Versus for this one, if I want to maintain the first two, then my projection capital P2, again, the other part of the identity matrix, which would be the 1, 0, 0, 0, 1, 0, 0, 0, 0. I don't want that third entry. And what he starts to get into is comparing these projection matrices, because if you're looking at these projection matrices and you're thinking about what we've learned from the first video set in section 1, these two, this is rank 1, this is rank 2, this has dimension 1, this has dimension 2. If I add those dimensions together, we get 3, which is the dimension of the 3 by 3 system that we're in. These are subspaces, and these create subspaces of R3. But not just that, they're orthogonal to each other because the z-axis is perpendicular to the x and y plane. And so all of those connections that we established with orthogonality are playing a big role here. That, again, they're not just orthogonal, but one is the orthogonal component of the other. And so we're starting to establish some connections essentially between these spaces. And you'll notice that B itself is a combination of these two projections, that if I add these two vectors together, it creates B. That's why these are orthogonal complements. They're perpendicular, but we can construct any vector in R3 as projections of a line in terms of z and the plane x, y. Again, we can create through these projections, but where it gets a little interesting is then when he starts looking at ultimately our goal in terms of page 152, that we put these basis vectors into the columns of A, and then now we're projecting onto the column space of A, and certainly z-axis is the column space of the 3 by 1 matrix, and it gives some examples. Again, if I call this A1 and A2, taking out the 0 entries, A3 is also in there. And this is where I'm going to kind of end the part 1 video at. Our problem is to project any vector B onto the column space of any m by n matrix. In other words, the goal is to be able to take any kind of vector and project it either onto a one-dimensional line, kind of counterintuitive in terms of saying it that way, or taking a vector and projecting it onto a new subspace. And how we find these projection matrices so that we can take essentially any vector and be able to project it onto those spaces, how much of that vector sits in that space. And all of it really depends on that orthogonality piece. That when I'm doing this projection, we're creating 90-degree angles here and here. I'll kind of do it like this. That we're always building out in terms of these right triangles. And so I'm going to draw this picture again when we get into the second piece, but notice again, there's essentially an error here of what's wrong with the projection, or essentially the distance between the two. And we're going to kind of use this concept to help build out our projection onto a line, which will then help us build out in terms of a subspace of a matrix.